I'm a data scientist at a gaming company, and I want to figure out whether the users of this game, when they tend to engage in more side quests, does that cause them to spend more money on in-game assets that they can be buying? And so there are potentially confounding variables out there that like things like being a member of a guild that you mentioned there. And so if we weren't collecting that guild data, we'd have to have more assumptions. We'd have to basically make the assumption that being in a guild doesn't matter or not. And so it seems like this has made clear that there's a lot of assumptions, more thinking potentially about your problem that you need to do if you're engaged in causal AI. So that's a great thing to understand about this. But to kind of get into the nuts and bolts, your book does a great job of using PyTorch code, using examples to make causal AI or causality in general, which is often a very theoretical, difficult to understand topic. Because of all of your examples and use of code in the book, it makes understanding causal AI more intuitive. And so let's say that you are the data scientist, Robert, at this gaming company. What Python tools would you use to then do causal AI? How would you model this in order to come up with a causal conclusion?
So one of the things that I had mentioned that I was trying to do with my book was to separate out the abstractions that have to do with statistics and computing, right? Like scale it up, algorithmic complexity from the causality. And what's cool about like the libraries that we have today is that they can actually help us if we're able to separate those abstractions. Then we get to focus on one thing while leaving the nuts and bolts to be handled essentially by the library. To some extent, you saw this. You mentioned you interviewed somebody who talked about Stan. And what's cool about Stan is that inference algorithm, Hamiltonian Monte Carlo, is, you can go in there and understand it. It's not, well, it is physics, but it's not rocket science. I'm like, well, it kind of is rocket science, but you can still kind of just specify your model, specify what are the parameters, what's the model, and as long as you satisfy a certain set of requirements, I think namely that all of these things have to be continuous. That's the inference will kind of just work for you without you having to go and implement your own inference algorithm. It's the same thing here, right? Where if you can, as long as you can kind of specify your causal assumptions in some cases in the form of a graph, for example, then you can rely on say graphical causal inference to the inference algorithms in from say probabilistic graphical models, or to kind of handle the inference there for you. If you're implementing it in PyTorch, like plenty of PyTorch examples in the book, as long as you can incorporate your causal assumptions in the structure of the model in your algorithm and write a kind of basic inference algorithm that has a differentiable loss function, then PyTorch is going to handle all of the nuts and bolts of the inference for you, right? That's kind of why we invented PyTorch, to say if I can differentiate it, then I can, if I can get a gradient, then I can just turn it into an inference problem there. And so that's why, so I do have examples there in PyTorch that are saying, okay, well, let's not worry about whether or not, we need to use linear regression here, or propensity scores, or double machine learning, or instrumental. These are all different types of kind of statistical methods for doing the inference you want. And you can learn all these things, great. And there's great books for that, right? I think I can name a couple off the top of my head, but you can also say, let's work with some libraries that are kind of just going to handle that stuff for us under the hood, and kind of treat it as either an objective function to be optimized, or as configuration in some a configuration parameter in some model specification, and then focus on our ability to think causally and write that thinking down in the form of a model, and focus on the actual domain that we're modeling as opposed to all the inference stuff that we need to do to get that to work. And so to answer your question, I talk a lot in the book about using deep probabilistic models like modeling like with libraries like Pyro, as well as some more conventional tools like the DoY from the broader PyY suite, which is a big collection of causal inference libraries. And so even in DoY, right, there are different types of statistical techniques that you can use to estimate a causal effect. But at the end of the day, you're thinking more about, what are your modeling assumptions, and can you answer the question given your assumptions in your data? And then if you can, you want to get to an answer, and then all of the various statistical approaches you can take to arrive at that answer given your assumptions in your data. You can kind of just toggle between them to see, which is giving you more stable results, for example.